These are the notes for the first part of 2.5. This will be the last section that we cover before we test on sections 2.1 to 2.5. It's called implicit differentiation. And remember, all these differentiation processes and rules that we've been learning are all geared towards the same end goal, which is to find the derivative of a function, which is a function that will give us the slope of the tangent line at any point on the function's graph. So we've got a new situation that's going to happen in section 2.5, and I'd like you to consider the equation x squared plus y squared equals 25. And what's different about this is both the x and the y are on the same side of the equal sign. It's not in the form y equals. Yes, on this one I could solve it for y easily, and I'm going to in a little bit. But for now, I'm just going to ask you the question, is it a function? And you would say no, based on what you've learned in pre-calculus and algebra 2. For it to be a function, that means that for every x, there's only one y value that goes with it. And for this one, there's 2, because the graph makes a circle, as we've learned in other math classes. So it'd be a circle with a center at 0, 0. And remember, this is equal to r squared, and it'd have a radius of 5. So it's a circle that kind of goes out to 5, up 5, left 5, down 5, and I'm just going to draw my graph like this. And you can see that fails the vertical line test, so it is not a function as it stands. But the question is, can we talk about the derivative at the point 1, 2, 3, 1, 2, 3, 4? And the point 3, 4 is on the circle because 3 squared plus 4 squared does equal 25. And so it's sitting here, and it's very possible to talk about the derivative there because I have a tangent line, and that tangent line right there has a slope. So can we talk about the derivative? Yes, we can. I'm going to go to the calculator and show you the dy dx option on that later, not right now. So there I'm sketching the tangent line through that point. Now, on the bottom of the screen here, it says, well, now solve that equation for y. So we had x squared plus y squared equals 25. And I'm going to solve that equation for y. And I get y squared is equal to 25 minus x squared. Taking the square root of both sides, and remember that means I can go plus or minus, I get this function, which is solved explicitly for y. And that plus or minus is what is again causing me to break the test for whether it's a function or not. For that y value, I have, for every x value, I have 2 y values. And you can see at 3, I also hit down here, which means, well, there's another tangent line down there at 3, negative 4. So what I'm going to do here is go to the next page. And it says now we're going to use the chain rule to find the derivative. So on the previous page, we had y equals the square root of 25 minus x squared, and it was plus or minus. So I'm going to use my chain rule to find dy dx. So the first thing I'm going to do is write this as 25 minus x squared to a power, and remember that power would be to the 1/2 since it was a square root function. So when I find the derivative, I'm going to use my chain rule, which says take the derivative of the outermost function with respect to x. So it would be 1/2 of 25 minus x squared. Drop it down 1. And then don't forget, we also have to take the derivative of the inside function. And technically, we would write it the derivative of 25 minus x squared with respect to x. And I know you guys have been doing that part in your head, and that's just fine. And the derivative of that is negative 2x. So when I multiply this out, my 2's would cancel, and it'd leave a negative x over, because this is to the negative power, the square root of 25 minus x squared. And this is a function which gives me the slope of the tangent line. And it says, well, we're supposed to find the slope of the tangent line when x equals 3. So when I go plug a 3 in here, do that in green, I'm going to get a negative 3 on the top over, on the bottom, I would have 25 minus negative 3 squared, the square root of it. which gives me negative 3/4. And remember I had that plus or minus out front also. So I'm going to go back to the picture on the previous page. What that's telling me is the slope of the tangent line at 3 could either be negative 3/4 or positive 3/4. And that had to do with my circle here. There were two tangent lines at 3. So this one, the slope of the tangent line is negative 3/4. And on this one over here, the slope of the tangent line is positive 3/4. And this is where I want to go to the graphing calculator and show you that too. So going to my graphing calculator here and going to the y equals button, again, because it's not a function, I can only enter the top or bottom half of the circle at a time. So I'm going to enter the top half just for demonstration purposes here. And my function was y equaled, and when we solved it, we said it was the square root of 25 minus x squared. And when I go graph this, you'll see the top part of my circle right here. And the reason it looks more like a ellipse or the top half of an oval is only because there's a bigger gap on the x-axis than they put on. It's because my screen is a rectangle and not a perfect square. So you're going to picture that as being a circle. And we just said that the slope of the tangent line at 3 was a negative 3/4. Well, let's verify that using our calculate the derivative option, number 6. And let's see what happens when we calculate that derivative when x equals 3. And I'll hit enter. And you'll notice it gives me here a negative 3/4. So that all matches. So nothing new here yet. Move it head of page. So it says, well, now what if we had a function, we had an equation which could not be solved for y easily, if at all? Can we still find the derivative? And the answer is yes, and that's what we're going to be working at today. I gave you the circle one so that I'm going to now do it another way. The circle one, actually, because I could solve it easily for y, I don't have to use the process in this section, but for demonstration purposes, I'm going to use that same function and just do it another way. So there's going to be a series of steps, and it's called implicit differentiation. You'll know when to use it because x and y are going to be on the same side of the equals sign. So, it's not going to always be like it has been up until now where it's been saying y equals or f of x equals. They're going to be on the same side like they are here. And I'm going to give you a series of steps on the next page, but I'm going to talk them through first. So the thought process behind implicit differentiation is this. The first thing you do is you take the derivative of both sides of the equation. Now, we have a lot of different notation for the derivative. We have dy dx, we have y prime, we have capital D, which means derivative with respect to x, and we've been using, and we have f prime of x. We've been using these three pretty regularly. I want to introduce this one for this process because it gets, I don't know what the word would be for it. The notation for implicit differentiation gets kind of complicated. The book shows it to you with this, which is really good for clarity, but in terms of writing, it's kind of labor intensive. This one is the easiest to use in terms of how much you have to write down, but people tend to make mistakes with this one, and this one's not practical for these purposes. So I've decided, after looking at several methods online, that I think the one you're going to make the least amount of errors with is if we use this notation for the derivative for implicit, and we're going to merge it with that, so that we get some of the organizational strengths of this one with some of the ease of that. So you're going to see me switching notation here, but I think when we're all done, which would be tomorrow, I think you'll be working with it pretty smoothly. So I'm going to take the derivative with respect to x of x squared plus y squared, and on the right-hand side, I'm going to take the derivative with respect to x of 25. And a key thing to note when you're doing derivatives is you need to have a variable match. And if not, you have the chain rule. This is what I mean by that. If you're taking the derivative of, say, let's do this one. Let's suppose you were just doing the derivative of y cubed, and it's with respect to x. Well, then you treat this as we've been treating like the function u when we've been doing our chain rule. You'd say, well, it's 3y squared using the power rule, but then I have to take the derivative of that inside function. You consider y a function of x. So you say it's 3y squared times the derivative of y with respect to x. Or as we've been writing it, 3y squared times y. So when the variables don't match, you treat it as the chain rule. So back over here, when I apply my differentiation rules for addition, I'd say the derivative with respect to x squared plus the derivative with respect to x of y squared equals, and the derivative of a constant regardless is always 0. The slope of the tangent line of a constant function is going to be 0 no matter what. Well, this one I do directly, and I just say, well, that's twice x. That's just the derivative of x squared. When the variables don't match, you use the chain rule. So you say it's plus 2y times the derivative of y, and this is where we're going to make that switch to y prime. So really what I do is I take the derivative of both sides, I use my differentiation rules, and when I don't have a matching variable, I treat it as the chain rule. And then keep in mind, I'm in search of the derivative, so I'm going to be solving this for y prime. So I say 2y times y prime is equal to negative 2x, which gives me y prime is equal to negative 2x over twice y. These cancel, and I get negative x over y. Now I'm going to repeat when we go back to that circle. Remember that I wanted you to find the derivative when x was equal to 3, and we did it on the graphing calculator, and when we did it by solving for y and just applying the chain rule, both methods, we got a negative 3 over 4. Well, look what happens on this one down here. I think I might have that process on the next page. Nope, I don't. So I'm going to go back a page. So what happens on this one here is, since it says it's negative x over y, is what my derivative was, well, then I would do a negative 3 over, and then remember the y value, when it's x squared plus y squared is equal to 25, well, that means that when y is a negative 3, my x is 4. So I get that negative 3/4, exactly as I got doing it on the graphing calculator. So now let's clean this up. And I think what I'm going to do is start a new video so I don't get cut off here. So I'm going to be done with this one. I'll start a new one. It'll be about 10 minutes long. Watch both of them, and I will restart in a moment.